everyone, back again with me, Jufian Alapolo, and I'm here once again to explain my Praktikum. But today is for my machine learning class, the third and the fourth Praktikum. So, first, the dataset that I'm using is named California Housing Price. This is dataset explain the median house prices for California districts derived from the 1990 census. So, the content of the dataset pertain to the house found in a given California district and some summary stats about and then the summary stats is based on the 1990 census data. This data is not clean and also need some processing step to do. So this is all the column that the dataset have: longitude, latitude, housing, median age, total rooms, total bedrooms, population, households, median income, median house value, ocean proximity. Also, this dataset is initially featured in the paper from Patrick R. Kelly and Ronald Berry, Sparse Spatial Autoregressions, Statistic and Probability, Letters 33.3 in 1997. Okay, now let's commence the initial inspection of our dataset structure and descriptive statistics. Upon loading the dataset into a structured data frame, we observe a total 2,040 observational entries spanning 10 distinct attributes. 9 of these variables are numerical, whilst one feature, ocean proximity, is categorical. Utilizing statistical summary function, we examine that the central tendency and dispersion metrics across all numerical features. For instance, we observe that the average housing median age across districts sits at approximately 28.6 years, while median household incomes range from a baseline of 0.49 up to 15.0 scale unit. Simultaneously, our frequency analysis of the moral variable, ocean proximity, reveals that the vast majority of housing blocks, specifically 9,136 units, are situated less than 1 hour from the ocean, followed closely by inland properties at 6,551 units. Identifying this foundational description is paramount before we proceeding to visualize our exploratory techniques. Okay, now we're going to turning our attention to the exploratory data visualization. We construct multiple graphical representation to uncover underlying empirical patterns. First, examining the distribution of our target variable, the median house value via Canadian CCT estimation reveals a slight right skew distribution alongside an artificial price cap at 500,000 threshold. Second, we plot a geospatial scatter map mapping latitude against longitude, where point size represent population density and color gradients reflects property valuations. This geographical mapping demonstrates a striking spatial phenomenon. Property valuation command extend premiums along the coastal metropolitan belts of the San Francisco Bay Area and Los Angeles, whereas inland district consistently exhibit substantially lower market value. Finally, in our present correlation matrix, qualifies the linear relationships among variables. Crucially, the median income emerges as the strongest linear predictor of housing price, boasting a robust positive correlation coefficient of 0.69. Conversely, graphical coordinates display slight negative linear relationships, highlighting the complex spatial dynamics at play. Okay, before we introducing statistical algorithm, the raw data must undergo rigorous preprocessing to ensure algorithmic stability and numerical consistency. Our preprocessing pipeline comprises in 3 steps. First, we're going to handle those missing values. Structural inspection detects exactly 207 missing values localized exclusively in the total tensors attribute. Rather than applying standard mean imputation, we avoid the skewness of this feature. Thus, the bedroom distributions exhibit pronounced right skewness due to outliers. We deploy the median imputation. The median serves as statistically robust estimator of central tendency, successfully eliminating null values without distorting the underlying data distribution. So, the next one we have here is second categorical encoding, which is mean to process the nominal categorical variable option proximity. We applied one-hot encoding. This transformation breaks down the five distinct categories into mutually exclusive binary columns of zeros and ones. Usually, this prevents regression model from misinterpreting nominal categories as possessing an arbitrary numerical hierarchy. For the third is the feature standardizations. Because our continuous predictors operate on vastly different scales, such a population count in thousands versus median income measured in single digits. We apply Z-score standardization using standard scalar. With this, we will transform all the independent numerical features to share a mean of 0 and a standard deviation of 1, preventing high magnitude variables from artificially dominating gradient optimization during model training. So, with the procedure set already prepared, we partitioned our observations into two independent subsets, 80% assigned to training set, comprising 16,512 rows, and 20% observed for testing, totaling 4,128 rows. A fixed random seed was implemented to guarantee strict scientific reproducibility. Because our target variable is continuous, standard classification metrics such as accuracy or confusion matrices are mathematically inapplicable. Instead, model efficiency is evaluated across three industry standard regression metrics. We have mean absolute error. We will going to use to measuring the apparent absolute magnitude of prediction errors in dollar terms. And we have root mean squared error. Applying the squared root to average squared errors can be imposing healthy penalties on large outlier prediction mistakes. Then we have the R2 score or the coefficient of determination, quantifying the exact proportion of variance in probability evaluation that our independent features successfully explain. So, after that, we're going to training our algorithm and see the evaluation of their performance. For our baseline, the multiple linear regressions, assuming a direct linear hyperplane between independent features and housing price, our linear regression baseline achieve an R to the point 2 score of 0.6254 or 62%.54. This average prediction error measured by MIE stood at $50,672.74, alongside an RMSE of 70,060. These figures clearly indicate that rigid linear formulation suffer from a moderate underfitting when confronted with complex real-world geospatial formations. And for our advanced model, random forest regressor, this one assembled backing architecture comprising of 100 parallel decision trees. The search offer randomized subsamples. Historical performance improvement was remarkable. The random forest model achieved an exceptional R to the power of 2 score of 0.81670, which is successfully explaining 81.70% of the variance in housing variations. Furthermore, error metrics plummeted significantly. The mean absolute error dropped to 31,643.66 cents, whilst the RMSI compressed to 48 1,675.82 cents. In conclusion, our empirical evaluation conclusively established the random forest register as the superior predictive architecture for the California housing dataset. By replacing a single linear hyperplane with multivariable ensemble of decision trees, we improve our model explanatory power by 19% and reduce the average pricing error by over $9,000 per dwelling. So that's it, my practicum for today. I hope that what I'm doing here can be understood by you guys who see this video. Don't forget to leave a like and comment below. See you guys in another video. Bye.